Now we turn specifically to the three largest terrestrial planets and look at the way their atmospheres have evolved over time. When we look at the evidence for the early atmospheres of Earth, Mars, and Venus, we find something very surprising. While they are currently very different from each other, in the past they were a lot more alike. We know from geological evidence that the Earth's early atmosphere had no oxygen in it, but it did have far more carbon dioxide than we see today. On Mars, we can tell that its atmosphere used to be much thicker than exists now, and there was more water on the surface and likely in the atmosphere. Carbon dioxide currently dominates what little air Mars has, and this was likely true in the past as well. For Venus, it's harder to tell what its early history was like, but we can get some clues from the chemistry of the atmosphere, which suggests that in the past Venus had a much thinner and wetter atmosphere than we see today. So if you had visited our solar system several billion years ago, you might have found three worlds with moderate pressure atmospheres, with a good temperature for liquid water, and dominated by carbon dioxide and possibly nitrogen. However, today we find one that is much too hot, one that is much too cold, and one that is just right. For that reason, planetary scientists call this the Goldilocks problem.
To understand how the Goldilocks problem developed, we need to look at how two key greenhouse gases behave in terrestrial planet atmospheres. The two gases we're going to focus on are water vapor and carbon dioxide. We'll look at how these gases cycle into and out of the Earth's atmosphere, and then see what went wrong with these cycles on Venus and Mars. We'll start with water vapor, which comes and goes from the atmosphere through what we know as the hydrological cycle, or more simply, the water cycle. The water cycle starts when water evaporates from the surface of the Earth and turns to water vapor. The humidity in the air is a measure of how much water vapor is in it. As this water vapor cools, it then condenses back into liquid or solid forms as clouds, rain, and snow. These return to the Earth and close the cycle. It takes energy to evaporate all that water and put it into the atmosphere. On the Earth, the source of this energy is the sun's light. The other key thing we can say about the water cycle is that it's in equilibrium. Over the course of a year, the same amount of water evaporates and then condenses again. However, in any active system like this, it's important to understand what happens when it gets out of equilibrium. That's what we'll look at next. When a system or object can change the conditions that in turn affect it, we call that a feedback system. The first kind of feedback, the one we just saw demonstrated with the water cycle, is called positive feedback. In positive feedback, a small change from equilibrium gets amplified so that it gets farther and farther from equilibrium as time goes on. In physics, the classic example of a positive feedback system is a ball balanced on top of a hill. So long as the ball is exactly balanced, it stays in one place. However, as soon as it moves away from the balance point, the forces acting on it keep pushing it further away from that point. So the ball gets farther and farther away from equilibrium. Positive feedback systems are fundamentally unstable. Often, even tiny perturbations can push them out of equilibrium, and once that happens, they can't get back to their starting point. There are several examples of positive feedback systems. A microphone, amplifier, and speaker combination can act this way. If the microphone is too close to the speaker, then even small sounds picked up by the microphone are amplified and emitted by the speaker, where they're picked up again by the microphone and made still louder by the amp. After several cycles through the system, the sound coming out of the speaker is a loud, annoying screech. We also just saw that the water cycle is a positive feedback system. As the temperature goes up, more water evaporates. But since water vapor is a greenhouse gas, putting more water vapor in the atmosphere warms the surface. This warmer surface increases the evaporation rate, and this makes the surface hotter still. a process that can keep going until all of the water has evaporated into the atmosphere. We call this a runaway greenhouse. The same thing can happen in the direction of cooler temperatures. If the surface is too cold, there's less evaporation and less water vapor in the atmosphere, which in turn makes the surface cooler still. This can continue until all of the water has condensed out of the atmosphere and frozen onto the surface. This is called runaway glaciation. So, the water cycle, like other positive feedback cycles, is an unstable system that tends to move away from equilibrium towards higher or lower temperatures.
The opposite of a positive feedback system is a negative feedback system. In negative feedback, when the system moves away from equilibrium, the conditions change so that it moves back towards equilibrium. Here, the classic physics example is a ball at the bottom of a valley. When you try to push the ball to one side or another, gravity pushes it right back towards its starting point. So negative feedback systems tend to be very stable. It's hard to get them out of equilibrium. A day-to-day example of a negative feedback system is a thermostat. If the temperature gets too warm, the thermostat turns on the air conditioning and cools it off. If the temperature gets too cool, the thermostat turns on the heater and warms it back up again. Here's Bruce back again to remind us that the terms positive and negative feedback here are not value judgments. Don't assume positive is good and negative is bad. These really just tell us the direction the system changes when it's perturbed. In fact, in many cases, the positive feedback systems are the ones with negative consequences, since they're so unstable.
Now we can look at the other important greenhouse gas that cycles in and out of the atmosphere, carbon dioxide. We're going to focus on the large-scale carbon cycle here. There are shorter-term changes in carbon dioxide connected to living things on Earth, but for the purpose of understanding the evolution of planetary atmospheres, we need to concentrate on the long-term part of the cycle. We'll start with carbon dioxide in the atmosphere. Whenever it rains, carbon dioxide is dissolved into raindrops and washed out of the air, carrying it into large bodies of water like the oceans. Much of this dissolved gas simply evaporates back into the atmosphere, but some is taken up by living organisms and eventually finds its way into the shells and bones of sea creatures. As the creatures die and their shells and bones fall downward, they build up into a thick layer on the ocean bottom. Eventually, the weight of overlying material converts these shells into carbon-rich rocks known as carbonates. If there was no life in the oceans, the dissolved carbon dioxide would build up to a high enough concentration that it would start reacting with dissolved minerals in the water to produce similar carbonates. On Earth, plate tectonics carries ocean crustal rocks deep into the mantle, where they're heated up and melted. When this happens to carbonates, they break down and release carbon dioxide gas. This gas escapes into the atmosphere through volcanism, closing the carbon cycle. Notice that the energy source for the carbon cycle is the planet's internal heat. That's what powers the tectonic and volcanic processes that allow carbon dioxide to be pumped into the atmosphere. However, the carbon cycle is also tied to the water cycle, since it depends on rainfall washing carbon dioxide out of the atmosphere.
Unlike the water cycle, the carbon cycle is a negative feedback system. To understand why, let's have a look at what happens if there was a little extra carbon dioxide in the atmosphere. Since carbon dioxide is a greenhouse gas, putting more of it in the atmosphere increases the temperature of the Earth. However, as we saw earlier, increasing the temperature also increases the amount of evaporation of water. The extra water vapor in the atmosphere causes increased rainfall, and this starts to wash the extra carbon dioxide out of the atmosphere. However, just washing it into the oceans isn't enough to reduce the available carbon dioxide, since much of it will simply be evaporated back into the atmosphere again. However, that extra carbon dioxide in the oceans makes it easier for carbon to be incorporated into living organisms, so it gets locked up in shells and carried to the ocean bottom. This is what finally reduces the total amount of carbon in the atmosphere and allows the temperature to come down again. Keep in mind that this last step is a long one. Typically, it takes thousands of years for the excess carbon to be removed to the ocean floor. In the evolution of a planet's atmosphere, this is a short time, but it's long for us humans. Now we'll come back to the Goldilocks problem. Why did Earth, Mars, and Venus come out so differently? We know that these two atmospheric cycles are working on Earth, so let's see what went wrong on Mars and Venus. On Mars, the most obvious problem was with the carbon cycle. Remember that the carbon cycle requires active volcanism to keep pumping carbon dioxide into the atmosphere. But on Mars, we know that volcanism slowed down drastically billions of years ago, so that now there's very little to no volcanism going on. The result is that the carbon cycle stopped on Mars a long time ago. With no new gas being pumped into the Martian atmosphere, the gas started to get thinner as water vapor froze, and other gases were lost to space through bombardment. As the air got thinner, the temperature dropped until we get to the Mars we see today, with a surface so cold that even carbon dioxide can freeze at the poles in winter. The name for this process is runaway glaciation, a planet where all of the remaining surface water is frozen and with no way of melting it again. Next, let's look at the opposite extreme.
We don't know much about the early history of Venus. The active surface geology on Venus has erased all but the last billion years of the planet's history. But atmospheric chemistry shows clues that in the past, Venus had a lot more water than it does today. Being closer to the Sun, it's likely that more of that water was in the atmosphere than we see here on Earth. If that's true, then it's possible that the water cycle simply overwhelmed the carbon cycle. With too much water in the atmosphere, the temperature went up, and this kept creating more greenhouse warming. Once most of the water was in the atmosphere, there wouldn't be enough rainfall to wash out carbon dioxide. Venus still has active volcanoes, so these keep adding greenhouse gases to the atmosphere, making the air ever thicker and hotter. This is a runaway greenhouse atmosphere. In the meantime, sunlight hitting water in the upper atmosphere split it into hydrogen and oxygen. The hydrogen is light enough to escape out to space, while the oxygen quickly binds with other gases or surface rocks. All of this has left Venus with the hot, thick, and dry atmosphere we see today. It's likely that most of the carbon on Venus is now trapped in its carbon dioxide atmosphere.